This video is going to be about differentiability. Basically, when is it possible to find the derivative of something, or when is it not possible? So let's start with an example. Take the square root of x. F of x equals the square root of x. You can show, using the definition of the derivative, the limit process, limit of the difference quotient, that f prime of x is 1 divided by 2 times the square root of x. I'm not going to show the proof of that right now, but we might do it in class. So the question I want to ask is, what happens at 0? Because certainly if I take any other point, right, I can imagine a tangent line. Great, slope of a tangent line. But as I approach 0 down here, at 0, the tangent line becomes sort of horizontal. Sorry. And of course, by horizontal, I mean vertical. Is this a vertical tangent line? If so, what is its slope? Undefined, right? So what is the derivative going to tell us? Well, let's see what happens. F prime of 0 would be 1 over 2 times the square root of 0. That's not a really valid thing to write, is it? That's undefined. So instead, let's ask using a limit. Let's explore this question using a limit. What is the limit as x approaches 0 from the right-hand side only, because the square root of negative numbers, we're calling that undefined. We're not dealing with complex numbers in this class. So what is the limit as x approaches 0 from the right of this f prime? It's 1 over 2 times the square root of x. Basically, what are the slopes if we come in from this side? Boop, 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 boop. Like, what are these slopes here going to be approaching as we get close to 0? That's the question. Well, this is something we should be able to figure out, right? Using our strategies we've learned before. For example, let's let u equal this. Let's just have u equal 2 times the square root of x. We can take the limit of that. The limit of as x approaches 0 from the right of 2 times the square root of x. This is just going to be 0, right? And it's also notable that if x is a positive number, the square root of x is a positive number. So we're approaching 0 from the positive side in particular. So our u would be approaching 0 from the right. I can rewrite this then. The limit is u approaches 0 from the right of 1 over u. And that's something we know about. This is just, here's the 1 over u function. And we're talking about this part. So this is equal to positive infinity, right? It is indeed undefined, but it's positive infinity. And so that's what's happening right there. At this x value of 0, where we have a vertical tangent line, we have an undefined slope. Because the slope is approaching positive infinity. Okay, that's what's happening. This is an example of a point where f of x is not differentiable. At 0. Okay, so that's that example. Now, let's talk about this idea of differentiable in a little more generality. First of all, a piece of vocabulary. We talk about the derivative of a function. That's the instantaneous rate of change. The process of finding a derivative is called differentiating. To find a derivative is to differentiate the function. To find a derivative of f, that is to differentiate the function. That's what that means. So differentiable means it's possible to differentiate, possible to find the derivative. Our definition for differentiable is that it's a function f. It's called differentiable at a particular value if f prime of that value exists. So when I say this function is not differentiable at 0, it's because f prime of 0 is undefined, right? It doesn't exist. Let's look at some other ways, or let's that way as well as some other ways that a function can be not differentiable. So this is going to be examples of points where a function is not differentiable. So one way that this can happen, what we've already examined, is the vertical tangent situation. Oh my goodness. Sometimes my computer gets confused about what I'm doing. So I'm going to draw a graph of this other than the one we just did. You can have functions that sort of go like that. And then at a point like right here, you have a vertical tangent line. So there's an example of a vertical tangent. This happens in things like the cube root of x, as well as the square root of x, as well as some and yeah, I almost said rational functions, but I'm not entirely sure about that. Certainly some kinds of trigonometric functions or inverse trigonometric functions exhibit this sort of behavior. So that's an example. Another case in which you can have something non-differentiable is what's called a corner or a cusp. There's a word, another vocab word for us, cusp. This would be where you have something like this, where at this point here, the question is, what is the tangent line? Sorry. What would the tangent lines be approaching? Are they approaching this slope or are they approaching this slope? Neither. In fact, actually what it is it's sort of like a jump, a sudden jump in the like the slopes. It produces a jump discontinuity in the derivative, in fact. We'll see examples of that later. Another case, this is like a corner. A cusp is when it sort of looks like that, and you kind of have it approaching infinity, perhaps. So in either of these cases, tangent slope is undefined. And then the third example is just anytime you have a discontinuity of really any type. So maybe you have a function that has a hole. Red I've been doing. It might be that the limit exists, but the function value doesn't. And so at that hole right there, there is no tangent line. When we find the equation of a tangent line, notice that there's two pieces of information we need. We need a slope and we need a point. This doesn't have a point. You can't calculate the slope without the point because the slope part of the definition requires that you have a defined value for the function. So if you have a hole in your curve, you can't have a tangent line there, and you can't calculate a derivative. Same happens when you have like a jump of some kind. Even if it is defined on one side or the other, what the heck is the tangent line? Is it going to be this tangent slope over here? Or are you going to approach from the other side and have a slope like this? It's unclear, right? It's again an undefined situation. And with vertical asymptote, you don't have any defined tangent slope. So basically, in order to have a function be differentiable, you need certain things. Differentiability requires several things. One, continuity. Can't be differentiable unless you're also continuous at the. Okay, so continuity is like a prerequisite for differentiability, but it's not sufficient because just being continuous isn't enough. This is an example right here. A graph that looks like that is continuous, right? You can draw that V or this cusp here. You can draw it, but it's not differentiable. Same here, right? You can draw that with, it's continuous. You can draw it without picking up the pen, but the derivative, that doesn't necessarily mean the derivative exists. So the other thing it requires is smoothness. And I'm gonna put that word out there. The word smooth does actually have a rigorous mathematical definition. It's a little bit beyond the scope of this class because it's more, as always, things are like a little more complicated than we tell you when we're teaching you things for the first time. So yeah, this is a little more complicated. Smooth has a very specific meaning, but basically I'm using it here to mean like no corners, no sharp corners, no pointy bits, right? So sometimes something looks like it has a pointy bit, but if you zoom in enough, you'll discover that it's a nice smooth curve. I'll show you a quick example of that as long as we're here. You pull this Desmos window open. It's a little bit too big right now. But if I do something like x power a bajillion, right? This looks clear bottom, doesn't it? That looks square. But if you zoom in far enough, hopefully I haven't made the power too big. Yeah, perfect. Look at this. If you zoom in far enough, you see that in fact it is a smooth transition from nearly horizontal to near, but not as near vertical. This is not actually horizontal, and this is not actually vertical over here. Okay, it's just we're very close to horizontal, very close to vertical, and we have something very close to a 90-degree angle. But none of those three things are actually the reality of the scenario. So this is what I mean by smooth. This is still differentiable despite it looking kind of square. Something that genuinely isn't differentiable though is the absolute value of x, which has this corner right here at the origin. And no matter how far I zoom in on this corner, it is always a corner. I will never discover that this is actually a smooth transition. This is a corner to the bitter end. All right, so that's something that's genuinely not differentiable right there. So that's what I mean by smooth. And then the third thing is to say, of course, that we don't have vertical tangents. That would be something we'd need to avoid as well. So those are our three requirements for differentiability.